Hello, Matthews Gatos here. In this lesson, we are going to cover section 5.3, concavity and points of inflection. Let's talk about what concavity is. Concavity describes the direction of a curve or how it bends. So you can see here, this is concave up and this is concave down. So like what we would do in 20-1, it opens up, so it's concave up. It opens down, so it's concave down. So let's say we want to draw tangent lines as I move across the curve and kind of see what is happening. So if I pick this parabola and I start drawing some tangent lines, like right there would be a tangent line, it's pretty steep. And as I move along here, do you notice that the tangent of these lines is getting less and less steep? The slopes are decreasing until they reach a slope of 0. Okay, so on the left-hand side, slopes decrease to 0. So we started out really steep and we decreased all the way down to 0. So let's see what happens on the right-hand side. So if I have a parabola that opens up here, starting on the right-hand side, I'm going to start at 0. And as I start to draw my tangents, you can see that they are increasing. Okay, so they're getting steeper and steeper and steeper from 0. So on the right-hand side, slopes increase from 0 on the right. So that's when it's concave up. Let's see what happens when it's concave down. So when it's concave down, you can see it's the same thing. So on the left-hand side, you can see the green one is where I start, green for go, and I'm going smaller and smaller, less steep and less steep until I get a slope of 0 right here. If I open down on this side here on the right, I start at a slope of 0 and I start to increase in the steepness of the lines. So it looks like it's true whether it's concave up or concave down. So on the left-hand side, slopes of the tangent lines decrease to 0, and on the right, they increase from 0. So concave up, the curve will lie above the tangent line. Let's go back over here. So when I had concave up here, you can see that the curve is above all of these tangent lines. So every tangent line that I have, the curve is above. So that's what concave up is. F of x lies above the tangent line. The slopes are increasing. The rate of change is positive. So we are happy. So concave up is happy. Concave down, f of x lies below the tangent line. See here? F of x lies below all of these tangent lines. And the slopes are therefore decreasing. The rate of change is negative. So concave up is happy, concave down is sad. And that's kind of the way that I look at concave up looks like the, a happy face smile, concave down looks like a frown. So the first derivative describes the direction of the function, the points where we're increasing or decreasing, but the second derivative is going to describe the rate of change, how the slopes are changing. So this is our test for concavity. This is going to help us when we curve sketch determine if a curve is concave up or down. If the second derivative is positive, that's good, we're happy, it's concave up. If the second derivative is less than 0, it's negative, it's sad, then the graph will be concave down. So the second derivative tells us concavity. The first derivative tells us slope. So let's just recap that. The first derivative is slope. The second derivative is the rate of change of slope, which is concavity. Okay, an inflection point. An inflection point, when we talked about this in Math 30-1, we talked about it kind of like a slide, like where it kind of just changes direction a little bit. So now with a calculus definition, we can really understand what that point of inflection is. So it's a point in the original domain. This is key here. It has to exist in the original domain. And it's the point where the second derivative changes from positive to negative or negative to positive. In other words, it changes from concave up to concave down or vice versa. It's usually the point where the second derivative is 0, but not always the case. That second derivative could be a local max or a min. So we just look at the change of direction. So for example, let's look on this curve here. So I'm going to look at where it's concave up, so that's happy. And then here I have concave down, which is a frown, sad. So right in the middle right there, this is your inflection point. So in this one here, we have concave down, that's part of a frown, and then concave up, part of a smile. Right in the middle there, that is your inflection point. Similarly here, this is concave up, and then here, this is concave down. Right in the middle is your inflection point. Now, in previous chapters, we talked about a cusp, and we talked about it where the graphs on each side approach a vertical tangent. So we said it was non-differentiable at a cusp. Well, in terms of concavity, we can now get a different definition. A cusp is the point on the graph where concave up meets concave up, or vice versa, concave down meets concave down. So if you look at this side here, I have concave down, that's part of a frown. And right in the middle there, that's not an inflection point because the concavity doesn't change. That's a cusp. On this one here, this is concave up. So these are both parts of the smile. And right in the middle there, not an inflection point, but a cusp. So let's put that together on this graph here. So we're going to use this graph, determine intervals of concave up and down, and label any points of inflection or cusps. So I'm going to look for all of my happy faces. Like there are the smiles. And then I'm going to look at my frowns. So I'm going to come up here a little bit more. There we are. And let's look at our frowns. So these are the sads. And those are concave down. Okay, so now that I've identified those, let's look at the points. So this point right here, concave up meets concave up. This is a cusp. Here, concave up meets concave down. That's an inflection point. And here, concave down meets concave down, so that is a cusp. Okay, so we can see that graphically, but let's look at how we do it algebraically. So algebraically, to determine your intervals of concavity and any points of inflection, we're going to find the second derivative, and we're going to set that to 0. Then we're going to use interval testing, just like we would for intervals of increase and decrease, but we're doing it with the second derivative now. We're looking for where it's concave up or down. So we're going to find those x values, those key points where the concavity changes. And then we're going to take that x value in the original function to find the coordinates of the inflection point. So looking at this example here, I've got f of x is this cubic function. Let's take the first derivative. So the first derivative would be 3x squared minus 6x plus 4. Now let's take the second derivative. 6x minus 6. So the second derivative is equal to 0. So if I set it equal to 0, that will happen when x equals 1. So x equal to 1 is our key value. So let's set up an interval at 1. Okay, so I have my second derivative. So my second derivative, let's write that out up here, in factored form would just be 6 times x minus 1. So if I look at this, the 6 is always positive, and x minus 1 is 0 right here. So to the left, the factor is negative. To the right, the factor is positive. So on the left-hand side, I have a negative, so that would be concave down. And on the right, I have two positives, which would be concave up. So if I want to list my intervals of concavity, I would say it's concave up, or sorry, why did I use blue? Let's try that again. Let's use it with my smile. So it's concave up on the interval 1 to positive infinity, and it's concave down on the interval negative infinity to positive 1. Now, because I changed concavity at 1, this is my inflection point. So when x equals 1, let's go into the original equation to figure out what the y value is. So I'm going to have 1 cubed minus 3 times 1 squared plus 4 times 1 minus 5. So that's going to be 1 minus 1 squared times 3 plus 4 times 1 minus 5. So altogether, that's negative 3. So I have my intervals of concavity, and I have an inflection point at 1 and negative 3. Okay, let's try another one. So here we have f of x. So the first thing I'm going to do is find the first derivative. So bringing the 5/3 down times the 3, I end up with 5x, and then decrease my power by 1. Minus, bring the 2/3 down, multiplied by the 15, and I get 10x to the -3. That's my first derivative. So now I want to find my second derivative. So bring the 2/3 down, multiplied by the 5, and decrease my exponent by 1. Bring the -1/3 down, multiplied by the -10 is positive 10/3. Oops, 10/3. There we are. And then decrease my power by 1. Okay, so let's factor this. So remember, when I factor, I don't want any fractions, so I'm going to take the 10/3 out, and then I'll take x to the smallest exponent out, which is -4/3. Okay, so dividing that, 10/3 divided by 10/3 is 1. X to the -1/3 divided by x to the -4/3 is, keep the base the same, subtract the exponents, positive 3/3, which is just 1. 10/3 divided by 10/3 is 1, and x to the -4/3 divided by x to the -4/3 is 1. So what I end up with altogether is 10 times x plus 1 in the numerator and 3x to the 4/3 in the denominator. Okay, so my second derivative equals 0 when, looking at the numerator, x equals -1. My second derivative equals undefined when x equals 0 in the denominator. Okay, so we're going to take this all together and we're going to set up an interval. So I'm just going to take this to the next page and we'll set up our interval. So on my interval, I'm going to have -1 and I'm going to have 0. Okay, so let's look at, first of all, my constant here of 10/3. So this is positive in every interval, so I'll just write that as positive. Okay, let's look at x plus 1. That's 0 at -1. So to the left, the factor is negative. To the right, the factor is positive. And let's look at our denominator. So our denominator, since we're raising it to an even power and then taking the cube root, by raising it to the even power, x to the 4, it will always be positive. And when I take the cube root, it'll just stay positive. Okay, so in my first interval here, I have 1 negative, so it's concave down. In my second interval here, they're all positive, so it's concave up. And also here, concave up. So let's write my intervals. So it's concave down in the interval from -infinity to -1. It's concave up. Now we can't say from -1 on because we have this 0 here. There are two different intervals where it's undefined. So we have to say from -1 to 0 or from 0 to positive infinity. Okay. So looking at this, I have a concavity change at -1, which makes that an inflection point. So let's go back to our original function and plug in 1. So y would equal to 3 times 1 to the 5/3 minus 15 times 1 to the 2/3. So plugging that in and working that out, it's going to be -3 take away 15, which is -18. So I have an inflection point at -1, -18. Okay, if you look at intervals number 2 and 3 here, they're both concave up. So this point is not an inflection point, but a cusp. So if I put 0 back into the original equation, I have 3 times 0 to the 5/3 minus 15 times 0 to the 2/3. Well, that just all works out to be 0. So I have a cusp at 0 and 0. Okay, looking at this one here. So this one here, the second derivative is a little tricky to find, so I've given it to you. So you have your original function. Now, I always look at that just to see if there's a domain restriction, because remember I said that inflection points have to be defined in the original function. So for this one here, there is no domain restriction because when I square a number, it's positive plus 1, it's always going to be positive, so my denominator is never going to be 0. So I have my second derivative, so what I'm going to do is I'm just going to factor it. So take out a GCF in the numerator, and my denominator can just stay like this because I can't factor that. So looking at this, I have a difference of squares in the numerator. So I have x minus root 3, x plus root 3, all over x squared plus 1 all cubed. Okay, so looking at this, my second derivative is never undefined because x is an element of the reals, but it is 0 at 0, positive root 3, and negative root 3. So those are my key values. So looking at a number line, I have negative root 3, 0, and root 3. Okay, so those are my key values. So let's look at each part of the second derivative and use our intervals to test. So let's start with 2x. So 2x is 0 right here. So to the left, this factor will be negative. To the right, it will be positive. This factor here is 0 at root 3. So to the left, it's negative, and to the right, it's positive. This one here is 0 at negative root 3. So to the left, it's negative. To the right, it's positive. And my denominator here, since I have something squared, it's going to be positive. Add 1, still positive. Raise to the 3, still positive. So this will always be positive. Okay, so let's look at my first interval. I have 3 negatives. So this is going to be negative, which is concave down. In the second interval, I have 2 positives. So that, or sorry, 2 negatives make a positive, which will be concave up. Here I have 1 negative, so that will be concave down. And all of these are positive, so it's going to be concave up. So let's look at concave down. So intervals of concavity. It's concave down from negative infinity to negative root 3, or from 0 to positive root 3. It's concave up between negative root 3 and 0, or root 3 and positive infinity. Okay, so let's look for where it's changing concavity. Those are inflection points. So I have an inflection point here, an inflection point here, and an inflection point here. They're all inflection points. So I'm going to take my x values and substitute them into my original function to figure out the y values that go with that. Okay, so if I take negative root 3 and I put it into my original equation, I'm going to have negative root 3 all over negative root 3 squared plus 1. So that means that my inflection point will be at negative root 3 and negative root 3 over 4. I do the same thing for 0. So y is going to equal to 0 over 0 squared plus 1. So that's going to be an inflection point at 0, 0. And then lastly, I do the same for positive root 3. And I get my inflection point at root 3 and root 3 over 4. Okay, for my last example here, again, I have f of x and I have my second derivative. So let's focus on the second derivative. Before I do that, let's see if I have any domain restrictions for f of x. And I can see I have a potential for division by 0. So I'll just note that x can't be 0. So that's true throughout the whole question. So looking at my second derivative, let's factor that. So it's 2, I go to 2, x squared minus 6 all over x to the 5. So this is a difference of squares. So it's 2x minus root 6, x plus root 6 all over x exponent 5. Okay, so I can see I have key values at root 6, negative root 6, and 0. So I just set up my number line. Negative root 6, 0, and root 6. So I'm going to note right away that x can't be 0. Okay, so what's happening at x equal to 0? Since it is a restriction, it is a vertical asymptote. Okay, because inflection points, remember, have to be in the original domain. So I know I'm going to mark that right away so I don't forget that. So now looking at all my intervals here. So I have the number 2, which is positive in all intervals. So I'll note that. Then I have x minus root 6, and that's 0 right here. So to the left it's negative, to the right it's positive. X plus root 6 is 0 right here. So to the left it's negative, to the right it's positive. And then x exponent 5 is 0 right there. So to the left it's negative and to the right it's positive. So let's put this all together. So in my first interval here I have 3 negatives, so it's concave down. Here I have 2 negatives, which make a positive, so it's concave up. In the third interval here I have 1 negative, so it's concave down. And then here this is concave up. So see what I'm talking about right here? You would think that because I go from concave up to down, it would be an inflection point, but it isn't. It's a vertical asymptote. Okay? So listing my intervals of concavity, I'm concave down from negative infinity to negative root 6, or from 0 to root 6. I'm concave up from negative root 6 to 0, or root 6 to positive infinity. Okay, so inflection points are going to be right here and right here. So putting it back into the original equation, y equals negative root 6 squared minus 1 all over negative root 6 cubed. So I will have an inflection point at negative root 6, and I'm going to have it at 5 over 6 root 6. Now, if you want to rationalize that, you can rationalize that as well. Probably better if I do. So that's going to be 5 root 6 over 36. Okay, I'm going to do the same thing for positive root 6, and it's going to end up being the same thing because I square it. So it's positive all over here. Oh, I think I made a boo-boo here. Just hold on. Yes, it's not the same. So this is negative root 6. This is negative. So this whole thing is negative. My mistake. All over root 6 cubed. So it's not the same, it's opposite sign. So this here is going to be positive root 6 and 5 over 6 root 6, which again I can rationalize to be 5 root 6 over 36. Okay, so looking at that all together, you can see my intervals of concavity and my inflection points. Okay, so to end this lesson, I just have a question for you. I want to know, why was the function so sad? Oh, he's so sad. Reason he was so sad? His dentist told him he had a concavity. Funny? I think so. Okay, so you guys can work on your textbook questions there attached, and if you have any questions, let me know. I hope this helped.